In section 14.7, you will apply double angle and half angle formulas. Our double angle and half angle formulas are listed on this page. We want to find the exact value of sine of 5 pi over 12 in our first example. So since 12 isn't a special angle, I'm going to rewrite that sine of 5 pi over 12 as 5 pi over 6 divided by 2, because they are equivalent. And then that way I have the sine of a half angle, and I can replace that with plus or minus the square root of 1 minus the cosine of that angle, 5 pi over 6. And 6 does create a special angle. So now I want to go to the coordinate plane and evaluate the cosine of 5 pi over 6. So I'll graph 5 pi over 6, and that's going to leave pi over 6 for my reference angle, and pi over 6 is equivalent to 30 degrees. So I want to label this 30, 60, 90 degree triangle in the second quadrant. So labels are 1, 2, the square root of 3, and the square root of 3 being negative. So now applying the definition of cosine to that angle, or that triangle, I've got adjacent over hypotenuse, or negative the square root of 3 over 2. Okay, now we need to decide if this answer is going to be positive or negative. And since we're really finding the sine of 5 pi over 12, and that's half of this angle, its terminal side would be in the first quadrant where all functions are positive. So I'm going to choose just to work with the positive square root. And in the numerator I've got double negative, so that's going to be a positive. I'm going to need a common denominator, so I'll write 1 as 2 over 2 plus the square root of 3 over 2. And then when I add in the numerator, I've got 2 plus the square root of 3 over my common denominator of 2. In the denominator, I don't want to divide by a fraction. I want to multiply by its reciprocal instead. So simplifying, I'm going to have 2 plus the square root of 3 over 2 times 2, which is 4. And then I can take the square root of the numerator, which is 2 plus the square root of 3, over the square root of the denominator, which is the square root of 4. So I'll leave my final answer as the square root of 2 plus the square root of 3 over 2. And this is the exact value of the sine of 5 pi over 12. In our second example here, we have the sine of a given as negative 1/3, and a is between 3 pi over 2 and 2 pi, so it's in the fourth quadrant, its terminal side. We want to find the cosine of 2a. So replacing the cosine of 2a with one of our three possibilities here, I would choose the one with just sine in it. So I can replace cosine of 2a with 1 minus 2 sine squared a, and that way, since the sine squared a is already given, I can substitute in for sine of a negative 1/3, and that'll be squared. So I've got 1 minus 2, and negative 1/3 squared is 1/9. So I've got negative 2/9 as my second term here when I multiply. So I'm going to write 1 as 9/9 so that I can subtract 2/9 from it and get a final answer of 7/9. This is the value of cosine of 2a. Okay, in our next example, we want to verify or prove that the sine of 3x is equal to sine of x times the quantity 4 cosine squared x minus 1. So I'm going to choose to change the left-hand side and make it look like the right-hand side, because I can write the sine of this triple angle as the sine of 2x plus x, and then I can use our sine of a sum formula so that I can expand and write this as the sine of 2x cosine x plus the cosine of 2x sine of x. And now I need to replace those double angles. So since there's only one choice for sine of x, I'll write that as 2 sine x cosine x times the cosine x that's there. And I'll replace the cosine squared x with 2 cosine squared x minus 1. And then that way I've got two terms and they have a common factor of sine x. So I'm going to factor sine x out of those two terms, and that's going to leave 2 cosine squared x in the first term. And in the second term I'll just have what's in parentheses, 2 cosine squared x minus 1. And now simplifying inside parentheses, I can add 2 cosine squared x to 2 cosine squared x and get 4 cosine squared x altogether minus 1. And that's what we needed to show, that the left-hand side could be simplified to sine x times the quantity 4 cosine squared x minus 1. So therefore, the left-hand side does equal the right-hand side. Okay, in our next example we want to simplify this expression, and this expression has double angles in it. So I'm going to start by replacing that sine of a double angle with 2 sine x cosine x. We only have one choice for that angle, or that function. In the denominator we can replace cosine of 2x with, I'll choose cosine squared x minus sine squared x, since I have both sine and cosine in the numerator. That might be a good choice. And then simplifying in the denominator, I'm going to replace 1 with the Pythagorean identity, sine squared x plus cosine squared x. And then I'll distribute that negative 1 through this quantity, so I have negative cosine squared x and a positive sine squared x. Okay, now simplifying more in the denominator, I've got cosine squared x and a negative cosine squared x, so they'll sum to 0. Then I have 1 sine squared x plus 1 sine squared x. That's 2 sine squared x altogether. And now I can cancel that factor of 2 top and bottom. I can also cancel a factor of sine x top and bottom, so I'm left with cosine x over sine x. And using the cotangent identity, I can replace that with cotangent x. So that expression simplifies to just cotangent x. Okay, in 2 we're going to solve an equation and find general solution of 2 sine of a half angle minus the square root of 3 equals 0. So I'm going to start by getting sine of a half angle alone. So 2 sine of x over 2 is going to equal the square root of 3. And then I'll divide both sides by 2, so sine of x over 2 is equal to the square root of 3 over 2. Now I'm going to have to replace my sine of a half angle, and I'll replace that with plus or minus the square root of 1 minus cosine x over 2. And now I want to get rid of that radical on the left, so I'm going to square both sides of this equation to get rid of the radical. And that radical times itself is going to be positive, and it's going to be what's inside, 1 minus cosine x over 2. And squaring square root of 3 over 2, square root of 3 times itself is 3, and 2 times itself is 4. Okay, so now I just want to get cosine x alone, so I'm going to multiply both sides by 2. So when I do that, 2's cancel on the left and 2's cancel on the right. So I'm left with 1 minus cosine x is equal to 3 halves. And now I need to subtract 1 from both sides. And when I subtract 1 from the right, I'll write it as 2 over 2 so that I have a common denominator. So negative cosine x is going to equal 3 halves minus 2 halves, which is 1 half. And I'll either need to multiply both sides by negative 1 or divide both sides by negative 1. so that cosine x is equal to negative 1/2. And now when I go to the coordinate plane, I'll ask where is the cosine negative, and that's going to be in the second quadrant and the third quadrant. So labeling that triangle in the second quadrant, cosine of x is adjacent over hypotenuse. So I recognize my triangle as 1, 2, the square root of 3. And across from the square root of 3 is a 60-degree angle. So I know that my reference angle is 60 degrees, or pi over 3. So now I can solve for x and name those terminal sides. In the second quadrant, a half rotation would be 3/3, so I'll back up 1/3, so I'm only going to rotate 2/3 pi to get to that terminal side. And in general, I'd want to add on 2 pi n so that I can circle the coordinate plane any number of times and return to that terminal side. In the fourth quadrant, or third quadrant, we're going 3/3 and 1/3 more, so that's a total of 4/3 pi plus 2 pi n in general. So there's my solution for this equation. Okay, our last example is another equation to solve. Cosine of 2x is equal to 5 sine squared x minus cosine squared x. And we don't need general solutions here, just once around the coordinate plane. So I'm going to replace cosine of 2x, since I have both sine and cosine on the other side. I'll replace it with cosine squared x minus, actually it's going to be sine squared x. No, cosine squared x. I was right the first time. Cosine squared x minus sine squared x is equal to 5 sine squared x minus cosine squared x. And then getting 0 on the left, I'll subtract cosine squared x from both sides and add sine squared x to both sides. So 5 sine squared x plus 1 sine squared x is 6 sine squared x. And negative cosine squared x and a negative cosine squared x is negative 2 cosine squared x. Okay, now I have an extra factor of 2 in every term, so I'm going to get rid of that to make my equation as simple as it can be. So I'll be left with 3 sine squared x minus cosine squared x, and I'm going to replace cosine squared x with the Pythagorean identity in order to have everything in terms of sine. Okay, and then distributing, I'll have 3 sine squared x minus 1 plus the sine squared x. So adding like terms, I'll have 4 sine squared x altogether minus 1. And now I just need to get sine squared x alone by adding 1 and dividing by 4. And then I'll have to take the square root of both sides to get just sine x. And when I do that, I get 2 solutions, plus or minus. The square root of 1 on top is 1, and the square root of 4 on the bottom is 2. So now I go to the coordinate plane and I ask where is the sign, both positive and negative. And that is going to be in all 4 quadrants. So I'm looking for 4 solutions or 4 terminal sides. And labeling the triangle in the first quadrant opposite over hypotenuse, I get 1, 2, the square root of 3. So I know that my reference angle here is a 30-degree angle, or pi over 6. And now I can list those solutions for x. Naming that first terminal side in the first quadrant, that's pi over 6. In the second quadrant, 6, 6 would be a half turn. I'm going to back up a 6, so only rotate 5, 6 pi to go to the terminal side in the second quadrant. In the third, I'm going to go 6, 6 and 1, 6 more. That's 7, 6 pi. And in the fourth quadrant, I'll go 6, 6, and full turn would be 12, 6, so I'll back up a 6, 11, 6 pi. Names that terminal side. So there's my 4 solutions to this equation once around the coordinate plane. Include with your notes of this video guided practice problems 2, 4, 6, 8, 11, and 13 on pages 956 and 959 of your textbook.